We will take a look on the bolt materials and how these are specified. So bolt materials are sometimes written as in terms of grades, and these grades, they tell us not only about the material but also heat treatment and their strengths. For example, table 8-9 and table 8-10 are applicable to the US customary units, and you can see that size with inclusive range is given, and then grade have been specified in the leftmost column. And against these grades, you will see that they've told us about minimum proof strength, tensile strength, and yield strength, and also which material is this bolt made up of, and then they've shown us the head marking. So with experience, one can identify that by counting these number of lines, one is able to guess which grade this one is, or vice versa. When the grade is given, then one can expect or identify which kind of bolt head markings will be available. Then come the ASTM designations. So numerical problems, you may find that it's written A307, 325 type 1, 325 type 2, 325 type 3. So depending upon this number, what you will do is come to this applicable table and identify these values which will be required to solve the numerical problems. And once again, you can see that for ASTM designations as well, the grades are also marked on the bolt heads. And the relatively simpler one is this, the metric mechanical property class, and once again you can see that the various strengths are given in megapascals. And usually these have to be marked on the head of the bolt. There is one more statement which is of interest. Manufacturers are supposed to take various samples out of the batches which they are making and then test those samples, and therefore they've specified that these are the minimum strengths and these are being exceeded by 99% of the fasteners, which means the reliability of this manufacturer's bolts is 99%. To compare the bolt specification methodology adopted for US customary units and the metric system. So you can identify that whenever a code is written in the problem statement that we've got a quarter inch 20 UNC-2 multiplied by 3 by 4 inch grade 5 hexagonal head bolt, each of this number or these letters, they mean something. Nominal diameter, threads per inches, then thread series, whether coarse or fine thread is being considered, class or fit, this is based on the tolerances, what is the length of the bolt, it may be required to determine the stiffness of the bolt, then material grade, this will give you the tensile strength or the proof strength, and then what type of head is being used for the bolt. And similarly for the metric bolts, nominal diameter, pitch, then thread making standard, thread profile standard, whatever you want to call it. Then you need to know this material class and once again the head type. So these are the two methods which we will see in our numerical problems, and you have to get yourself familiarized with these specifications. The stress strain curve for an arbitrary steel is shown, and we can identify the strain corresponding to yield point is much smaller than the strain corresponding to the fracture point. On the other hand, for the bolt material, we identify that the strain corresponding to the proof strength, if we may write this, is not very small as compared with the strain corresponding to the ultimate strength. Okay, the load corresponding to this point or corresponding to the proof strength is termed as proof load, and then sometimes it's also called as the proportional limit. For good bolt materials, we perform the processing and heat treatments to achieve a condition where this curve continues to rise and the distance, or rather difference, between proof and ultimate strength is small. Let's consider that we had two pipes which were joined together with the help of a number of bolts. So pipe 1 and pipe 2 have been joined with the help of a number of bolts, and these are symbolically or schematically represented by round symbols. Then we isolate one such bolt and the members or the plates, and we say that the load, total load, was being represented by P subscript total, and the load carried by one bolt and the pressure cone is P, which is equal to this P total over a number of bolts. Okay, and then we have seen how we can represent this bolted joint as a combination of springs. Kp represents spring constant or stiffness of bolt, and Km represents stiffness of members. And this stiffness we had determined by considering the cones being compressed in the grip. Now, when we are applying a preload on the bolt, okay, first of all, you can imagine that preload is necessary. For example, if we consider the wheels of an automobile, these wheels have to be joined, and then these have to be joined with the help of bolts, and there is some preload which is necessary so that under the influence of vibrations and rotations, the wheels do not untie themselves and come off the vehicle. So we need preload for this joint to function. Now during preload, we've seen that bolt is stretched. Initially, bolt is free of any load, any force, and when we twist the nut, let's imagine in this direction, this is going to cause this bolt to elongate. and the members in the grip will be compressed. When this external load is applied, we pull these pipes apart and this P total gets transferred into one bolt and the plates, and we've termed this as simple P. So this causes the bolt to stretch an additional amount, and we've represented this by the Greek letter delta, and the members are unstretched with the same amount delta. Right. Now let's define some symbols which we will need for the subsequent equations development. So we've got this initial load, we'll represent with this by F subscript I, then total load, and then external load per bolt and the pressure cone. Then this P is equal to P subscript B plus P subscript M. That is, some portion of this load will be carried by the bolt and the remaining will be carried by the members. Okay, the resultant bolt load will be summation of this portion of load carried by bolt and the initial load, while resultant load on members will be equal to load carried by the member, subtracted from it will be the initial load. Then we define this C as a fraction of external load carried by the bolt, and N is number of bolts in the joint. So let's make this consistent. Let's see the significance of stiffness constant. We start off by the extensions, and we've said that the same extension takes place in the bolt and the member. So equating these two extensions, we represent the load carried by the member in terms of the stiffnesses and the load carried by the bolt. Then we try to bring in the total load carried by the bolts and the members, and we define this joint stiffness constant in terms of stiffnesses of the bolt and the members. So this C indicates the proportion of external load being carried by the bolt, and usually the good design target is around 0.2, that is 20% of load will be carried by the bolt and 80% of the load will be carried by the members. Bolt load is given by equation A-24, and the resultant load on members is given by equation 8-25. Both these equations are applicable only when the members are experiencing some compression. As soon as the members stop experiencing any compression, or the force on the members becomes equal to 0, or it becomes above 0, or the members transition from compression to tension, we say that the joint has failed. So joint failure occurs when the force on members becomes equal to 0 or positive. It doesn't mean that the bolt is going to be broken. It may be broken, it may not be broken, but our equation will predict the failure as soon as the force on the members becomes zero or it transitions to the tension. So we've said that we need some bolt preload for a joint to function, as this bolt preload will keep the members in compression. So the best way or the ideal way is by relating the measured bolt elongation and the calculated stiffness. From the dimensions of the bolt, we calculate the stiffness, and if we could measure the elongation in the bolt. So let's imagine we have a bolt which is being stretched due to the application of external torque, and this is causing this bolt to elongate, and we could place some measuring instrument on this bolt and measure the elongation delta. Now this is easier said than done, because placing a measuring instrument on each and every bolt, when most of the times the bolts are inside the holes and these cannot be approached externally, it's very impractical. Then we try for the alternatives, and the most commonly used alternative is to apply the torque wrench. What this wrench does is it allows the user to apply only a fixed value of torque. So even though the force could be applied higher than the required torque, the torque wrench would slip, and only where this torque wrench has been previously set, that amount of torque will be applied. Now how much torque we need to apply? For this, we try to find a relationship which relates this applied torque with the bolt preload. Now we turn to equations 8-5 and 8-6, and we replace the force with the initial bolt preload. And then once again we've replaced tan lambda with the appropriate variables, and the remaining symbols, these have been defined on the lower side of the slide. Let's consider that for the figure shown on the right hand side, this nut is stationary and we are twisting the bolt in this direction, and by some magic we know the initial load which we want to generate. So the torque required to generate this initial load can be determined from equation C, and we've reached to equation C by simplifying equation B by utilizing this diameter of collar as 1.25 times the nominal diameter. So the development you can see here. Then we term all of this as K and end up with equation 8-27, which relates the bolt preload with the applied torque. It means that if we know the torque application capacity, we can find out the preload which will be generated, or if we know how much preload has to be generated in one bolt, we can determine the corresponding torque setting for the torque wrench. Table 8-15 gives us some torque factors for various bolt conditions. So from the problem statement, you will have to identify which kind of bolt condition we are talking about, and then select the appropriate value for K if I tell you to estimate torque. And if I use the terms such as calculate, equations 8-26 and 8-27 will be applicable. You may have noticed that when you bring your car or a motorbike for maintenance, the technician, after performing the maintenance, while he is putting together all the pieces which are to be bolted, he may apply some lubricant on the bolts. So the logic for this is that some people conducted some experiments, and for these experiments they did not apply any lubricating oil on the bolt, and they tightened the bolt. So what they found out was that the mean value for the tests was 34.3 kilonewtons and the standard deviation was 4.91 kilonewtons. Then they performed the same experiment by lubricating the bolts, and then they noticed that the average value for the induced load or the preload did not change, or the change was very little, but the standard deviation was significantly reduced. So if the technician does not apply the lubricant, you should ask them to apply. Another benefit for application of the lubricant is, so far we have considered that when we twist the nut, the effect of friction is insignificant. So if we do not apply the lubrication and twist the nut, there is a possibility that this bolt might get broken due to excessive shear being generated as a result of the frictional force. One more consideration while making these bolted joints, usually we prefer to keep either the bolt or the nut stationary and twist the other component. Once again, this avoids the excessive shear being generated in the shank of the bolt.